At the first lecture, we were looking at liquid surfaces and the forces they can exert. That was preparation for a measurement of a size of a single molecule. You may have seen it prepared here. Now we hope we're ready. We have as a reserve there a tray of water, and here an overflowing tray of water painted black, waxed, so that I can clean the surface. I'll put a little waterproof powder there. They're the spores of a mushroom of sorts, and I'll move the boom along, and the powder is carried across. It's a clean surface. I'll move the other boom, never mind if the water overflows, and clean off that too. Then we're going to put a single tiny drop of olive oil there. We'll see if we can show you the size of the drop. I have a scale measured in 0.5 millimeters. And I will hold the drop just next to the scale with a trembling hand so we lost the drop. Doesn't matter, we'll find another. I think that will just about do. About right. Now we'll carry that very carefully across, powder the surface, and see how it spreads. Now I'd like to make a rough measurement. That's 20 centimeters between my fingers, that's 25 between my fingers, and it's now spread to an uneven shape. I can try very quickly indeed a small drop on the other tray since it's there. We'll just see what it does. Mr. Coates, will you get me a small drop? This is called division of responsibility. Ready? Notice how much quicker the expert hand and eye can be. Ready? That's a much nicer circle. Thank you, Mr. Coates. Then, in that case, it's about 10, 20, 25 centimeters across. 25 centimeters across. I'm going to see what we can do with that. We can't do anything, just say it's a thing you measured, unless we make a guess. I'm going to make a guess that was made in the last century, that olive oil spreads till it is 1 molecule high, like a velvet carpet, like the pile of a carpet. And so I'm going to calculate on the basis of that guess what would happen if a little drop, 0.5 millimeter in diameter, spreads to 25 centimeter circle. Now that's going to be rather a nuisance to do, so what we're going to do is to box the little 0.5 millimeter drop in a cubical box, 0.5 millimeter by 0.5 millimeter by 0.5 millimeter. That is a 20th of a centimeter by a 20th of a centimeter by a 20th. And then we're going to box the round patch, the second one I think was a better test, the round patch 25 centimeters into a square, 25 by 25, like that. And then we can do the arithmetic more easily. We're going to do that arithmetic, and so we have the little cubical box which contains one oil drop, a half millimeter, a half millimeter, a half millimeter. Those are millimeters. And its volume, if you put it in a box, is 1/20th of a centimeter times 1/20th of a centimeter times 1/20th. It isn't going to be all arithmetic, don't worry, no headache. And that spreads into a beautiful circle which we will box into a square 25 centimeters across, and therefore we say we have here 25 times 25, and what else? Here's the whole circle, and its height is the height of one molecule high, which we'll call h. And so it's 25 times 25 times h, and those two are the same if the oil has not changed its volume. And so h must be 1/20th, 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 1/25th, and 1/25th. So it is 1/20 times 20 times 20 times 25 times 25. 20 times 25 is 50. 20 times 25 is 500. And 20 times... Why didn't somebody stop me? It's a method of finding out if you're awake. Another 20 times 25 is another 500. And we're left with one more 20. And so we'll say 20 times that is 5,000, 10,000. So it's 1/500 times 10,000 of a meter, of a centimeter. That's the height of one molecule. If you like, ask your chemical friends about olive oil. It has 3 fingers to it, each about a dozen atoms long. So you take 1/12 of that, and that will give you the sort of size of an atom. Now that's a thing to do at home when other people aren't bothering you, and you can find the size of a molecule of oil that way for yourself. You can use lots of ordinary, even face powder will do more or less. I want to go on from that to a case of boiling water, which we were ready with last time, but we weren't quite sure. And we're boiling the water here in this large flask. How do you know it's boiling? Boiling is nothing but bubbles. Do you agree? Bubbles, that's all it is. Bubbles of vapor. And there it is. You can tell it's boiling because it's bubbling. You can also tell it because it's very hot. Now we're going to take away the atmosphere here and make it easier for it to boil, because the bubble has to grow. And if the air outside presses down on it, it stops it growing until it reaches a boiling temperature when its molecules are very violent. But now we're going to run our pump. We've run it from 15 pounds a square inch down to 8 pounds. Pump away, Mr. Coates. Oh, it's a little cooler. That's right. Continue the pump, please. Will it go any more?
That's better.
It's down to half an atmosphere. Will it do any better or not?
No, I think that's just matching.
That's all it'll do?
Yes.
All right. It's boiling well enough without the Bunsen burner there, because it's taking enough heat from the glass. It's down to 5 pounds a square inch. That's as far as that pump will carry it, I think. Let's undo that, therefore. That's it. We'll pour out our beautiful boiling water that was still boiling. Yes, it's all right. You want to try? You want to try? It's very hot. Mr. Coates will offer it to you. Just try it carefully, very gently. Thank you. Thank you very much. you get a reward of ice cream. But it isn't going to be ice cream. At a later lecture, we'll go still lower till we have water which is boiling and freezing at the same time. Water, ice, and steam all together. And you'll get the piece of ice from that if you remind me. It won't be till a later lecture. We have now a very special experiment in which we have carbon dioxide liquid in a little tube, and we hope it's going to turn into a gas, because above a certain temperature its molecules move so fast that they're above escape velocity and they just escape into the whole thing as a gas. We're going to look at this with a special camera. It's in a little tube here, and I hope you will see it on the monitor screens. We're now pumping hot water around it, and it's going up to this magic temperature called critical temperature. And I can still see the little mark there where the liquid surface is. We are putting cold water in, I beg your pardon, very hot water in, and presently you'll see the surface, liquid surface, harder to see, quite difficult to see soon. I'm going to put a gentle thermometer in.
It's gone.
It's practically gone. It's going, it's going, it's gone. It's completely disappeared. You can't see any liquid anymore. It's reached the temperature of a gas, and nothing more can happen in liquid then with that particular stuff. Now we're going to cool it in ice water. Watch it carefully. It'll suddenly get down to the temperature of making a liquid again. There'll be a rainfall of white fog condensing down, and you'll see it happen. It's worth seeing. While you're waiting, we are preparing another experiment, which is to look at air molecules bombarding something. It's coming.
There it is.
There it is. Can you see the fog coming down and the liquid building up? It's a very important temperature for modern measurements in radioactivity, in nuclear physics, where you have a bubble chamber. What does the air pressure do to things? I want to show you some effects of air pressure. Mr. Coates has a pump here, and he's going to pump out air from this large tin box. Start it and stop it. Won't stop, won't stop. Before we proceed further, I want to talk to you a little bit about the way the pump works. A pump doesn't suck, except that we talk of it sucking just as a technical term. All a pump does is to offer opportunities to go abroad. It's just like the way of getting people out of the top floor of a tall shop, a department store. The lift goes up to the top and opens, and the people are wandering around, and some people, just because they aren't thinking, wander into the lift. It's known as diffusion of population. And the people who wander in are shut in quickly, shut the lift, down goes the lift, out go the customers by some method or other. Up goes the lift, open the doors, in wander more people, down goes the lift, out go the customers, up goes the lift, and so on. That's how the pump works. Except for customers, it's air molecules. Now, Mr. Coates, would you please turn on the pump, which works just like that, driven by an electric motor.
It's going.
It's going.
I'm struggling the pump.
You going any further?
No, it's not going any further.
No. All right. Then I'd like to show you the next experiment, which starts with a picture of long ago. An experiment was tried to see if air exerts an important pressure. If we have this slide, you will see the horses trying to pull apart two cups which were just placed together. Those two huge cups were dragged apart by horses, and they could not succeed when the air had been pumped out. Now you may see Mr. Coates doing the same thing, but we should like some strong volunteers. Oh my, what a difficult question. We'll take you two on this side, and we'll take you two on this side, and Mr. Coates will say, come on out, will say if he needs more help. Do you need more of them? All right. Here are the two cups. They've been stuck together with Vaseline.
Put that rope. And to this side. Right, ready? Take the strain. Lenny, move it up. Right, heave. Come on. The girls are winning. Come on. The girls are winning.
Come on, red jersey, come and help on this side, quick.
There we are.
Quick!
Boys are winning now, it's not fair.
Okay.
Just a moment.
Now, wait a minute while Mr. Coates lets the atmosphere inside.
Now, Paul. It's all right.
Thank you.
Okay.
We sometimes measure the air pressure with a mercury barometer, and we have a large one up here which we're going to operate. Now, it's being pumped up there just to make a vacuum. The pump is working down on the floor. Turn the pump on, please. Oh, wait a minute, will it go up and hurt? We don't want mercury in the pump.
No, I think it'll be okay.
All right. Remarkable. 70, 71, 2, 3, 4, 5, 3/4 of a metre. 76 if you wanted to read like the book, but that depends on the weather, of course. There isn't any weather in the book, though. 3/4 of a metre of mercury. Would you let the vacuum out? We're going to try that presently with a water barometer instead, so we show you that just for fun. I'm going to tell you a story now. About air pressure. Suppose we wanted to think of air pressure as just the ocean of air above us, which sits on us. That's one view. Another one is, suppose you think of it as molecules of air pounding. Quite roughly like that. Like that. I'll try it on you. Here is a person on the ground being pounded by air, and air molecules are coming pounding down like that. I wonder how fast those molecules are moving. We're going to find out how fast those are moving by seeing what that atmosphere above is like. But first of all, we want you to see an example of something pounding that's big enough to see. We have way up there a supply of small steel balls about the size of a thumbnail, and they're going to hit an anvil here, and they're going to bounce off. Do you want to take that projector out of the way? Now, just to be quite sure, I'm going to ask the front row there to move out to the sides for a few minutes. Nobody will take your seats. That's all right. That's all right. Anywhere there. That's right. They're all right. That's all right. Right. Would you please drop one ball on the anvil, please? how do you know that they're exerting a pressure on that anvil? I'll take this holding weight off. This is a seesaw like that. And you see it's a seesaw? So that if I put these coins from there over to here, the pointer will go up a bit. Now we put the coins back there till the pointer goes back home. About there. There's a magnet there to get rid of too much bouncing. It's a special kind of free friction. And now we're ready with the whole thing ready to tip about an axle here. So if you now send a stream of balls down, this is why we move people, they're going to bounce more easily. Ready? Watch the pointer. That's it. Now, did you see that while they were falling here, they exerted a force? And that's how atmospheric pressure works. That's a model of that. Now, we have here another kind of model, which is just for fun, but it's preparation for something later on. This is a jet of water drops, not steel balls anymore, but drops of water. Loose the line, the electrics. We're going to project the picture on here. So if you hold this screen about there, that's good. Now, if you look at the screen, can you see that we've practically frozen these drops of water because we're flashing a light at the same rate that the drops are coming out? We've got a little electromagnet which is suggesting to this jet of water the drops should come out 100 a second. And we are flashing light at the equivalent speed, so it seems to freeze them. They're a little bit too excited. We'll cut them down slightly. There's that's better. Now there's a parabola of drops of water, and if we stop the flashing light, you will see that you just see a screen without being able to see very much. That is a preparation for a later experiment with drops of water illustrating the electrons in a television tube or an oscilloscope tube, because we shall have electrically charged drops of water later on. Now I want to come back to my story of people being pounded on here on Earth by air molecules and see what we can find out by imagining a certain change. I'm going to imagine that you, lying on the Earth here, are bombarded by molecules. Is that clear enough? Oh, yes. That you're bombarded by molecules, but instead of having the air above, you have only water above. Well, first of all, mercury above. There's mercury. An atmosphere of mercury, you've swum down to the bottom on the surface of the Earth here, and when you have swum down to there, you're pounded on by mercury atoms instead of air, and so there is nothing up here above. There's zero vacuum up there, and down there you feel the same pressure if the mercury is how high? How much mercury? How high? Oh no, that's in the books. Roughly, please. This is desperate physics. Get on. Well, 75 is what I measured, but the quick number is 3/4 of a meter. 3/4 of a meter. Now we're going to change from that, please, to a water atmosphere above you. How high has that got to be? Well, you may not know about 13.6. We better find out how much the water barometer does. So let us make a water barometer now. We have a bucket of water there, and this tall pipe goes right up there, marked every meter by a red stripe. Up it goes, please. Mr. Coates, are you up there? You ready? Look, up it goes. You shouldn't sneeze at a water barometer. Up at the top it'll boil. It'll froth a bit. Stopped. Where's it got to?
It's about 10 meters.
10 meters. 10 meters for the water barometer. All right, now we know.
Shall we let the vacuum down?
Oh, yes. Let the water run down. Let the vacuum escape. Meters of water over you instead of the atmosphere. So that we now got a new imaginary story, that you're at the bottom of an ocean of water, 10 meters of water, 34 feet of water, and that would press on you just as much as the atmosphere. But now let's change from that to air as thick as the air in this room, and see how that would go. For that I must weigh some air and weigh some water, please. So I have a very special weighing machine. It has the guts of an electric motor inside, curiously enough. I can make it read 0 by telling it to, and you will see the numbers there up on the monitors. I will also read them aloud to you, because there is a danger that with monochrome television sets you might not see those numbers easily. Mr. Coates, can I have this tall jar, please? Good, thank you. I put that on there, and we get all kinds of stories of how much it reads, but we tell the machine to go back to 0. Don't count that. It just says 0, or 1/10 of a gram. That last figure is 1/10 of a gram. Now we're going to pump the air out of that and see how much air we've pumped out. You all right on this? You can hear the pump working away. Thank you. It settles down, takes a little time, it's wobbling. 2.9, 2.8, 2.7, 2.6, 2.7, 2.8, 2.7, about 2.7 grams negative. That's only because we started at 0. That's what we've taken out. And so we've taken out say 2.7 grams of of air, and now we're going to see what we can do with water. No, not on there, it'll weigh it. Now, let the water in instead of the vacuum. A lot of air dissolved in the water will appear. There'll be a small bubble left, therefore, up at the top. But that I can't help. We're making rough measurements anyway. That's pretty good, Mr. Coates. Let's see how much we've taken out. 1861.9. 1862. 1862. I need a round number. I'm getting tired of these fancy numbers. What's the round number nearest to 1862? 2,000. All right, we'll take 2,000. Thank you for the suggestion. 2,000 grams of water in the place of how many grams of air? Air, how much was it? No, it was lower than that. 2.7 or 8. I'll take it 7 if you like. And water? 2,000. So 10 meters for the water barometer has to be increased for an air barometer in the proportion of 2,000 to 2.7. And so for air, as thick as the air here all the way up, it doesn't really do that, it gets thinner and thinner, but we'll take it all the way up the same, will be 10 meters multiplied by 2,000 over 2.7. Now we have to do some arithmetic. What is that going to come to? But 2.7, we will double that, and it's going to come to 5.4, and we'll double that and say point times 2 there, and we'll double that, 10.8, 10.8 times 2 again. And so we've got 10.8. Well, I want to make life quick and easy, so I'm going to call it 10. So I have 10 over 10, very providential, isn't it? Times 2,000 times 2 times 2, which is 8,000. So it's 8,000 meters, 8 kilometers of thick, gooey air like the air around us, all the way up, and then a vacuum above. Well, now what good's that? Let's put it to some use. You haven't seen what's going to happen yet. We have now the top of the atmosphere here. I'm sorry, I want more space. We have the top of the atmosphere up here at 8,000 meters. And up at the top, there's nothing else. Here's you downstairs being bombarded. And we have up here one molecule and air all the way up, but nothing higher. Up here, it's a vacuum. So we'll take one molecule. We have to hold him up there. We have to hold him up there, so we have an angel to do it, like this. So we'll draw the angel there. I think we better have him there. The angel is here. He holds him like that, and he drops him suddenly. The angel lets go. And this goes faster and faster and faster down through the air, like that, and just manages to hit your head, bang. Then he bounces up, since you're elastic, and goes up again, and up, and up, and up, and up, and then he turns over and comes down again. We don't need the angel, he can fly away. How fast is he going when he hits you? Well, we don't know. We'll have to make a measurement about something falling. Mr. Coates has something that's going to fall from way up there, you'll see in a moment, right up there, there's a white ball, which is 5 meters above the ground. So we're going to find out what happens at 5 meters. 5 meters fall. We have a clock here which will tell you when the ball arrives. I have 2 sheets of kitchen foil which are kept quite separate from each other and will be bashed by the ball into contact. There's an undersheet and an upper sheet and sand underneath to break the fall. So that this will be our contact for the arrival time, arrival instant. The leaving instant is done by a little switch there, and my clock will be here. When we break the connection, the clock will start and run like that. Listen to its beating seconds. It's 1 second for every half turn. Now we tell it to go back to 0, please. It'll do that. Now the clock is ready. We've got 5 meters of fall. Are you ready? 5, 4, 3, 2, 1, go! And it's exactly 1 second. 5 meters fall in 1 second. But that isn't what we wanted. We wanted 8,000 meters. How long does that take? I'm not going to use a formula. I'm going to cheat and then satisfy you. I cheat by saying I know the answer. That's how mathematicians work things out. So I'm going to say I know the answer is 40 seconds. And I'm going to find out whether 40 seconds will do or not. You see, 40 seconds is 40 times as long as 1 second. And so you've got 40 times as long to gain speed. And you will therefore, in that time, gain 40 times the set of speeds. And at the same time, you'll have 40 times the length of time to spend those speeds in. And so you'll go 40 times 40 times what you did there, times 5 meters. So that's how far you would go if you fell for 40 seconds because of that. And then you look at this. This is 40 times 40. 5 times 40 is 200. 40 times 200 is 8,000. And that's what I told you we were going to get. So I'm right, it was 40 seconds. In 5 meters, you fell in 1 second. The average speed was 5 meters per second. But the final speed, from 0 to the full final speed, will be twice that. But then you average to 5, and so it is 10 meters per second. And so the average here, with 40 seconds, will be 40 seconds, 40 times 10 meters per second. That's how fast the air molecule is falling when it gets here. And so it's 40 times 10 meters per second, 400 meters per second. That's an underestimate, 20% or 30% wrong, because I've been cutting corners. And it's a quick, cheap method. But don't let your friends despise it. Your friendly physicist will say it's a terrible method, cutting corners. It's wrong. It's not. It was used by the great physicist Boltzmann to work out the distribution of speeds of air molecules. And this is Boltzmann for babies. This is a baby Boltzmann calculation. And they do move about 400, well, do they move 400 meters a second? That's 1,300 feet a second. Do air molecules really hit me 1,300 feet per second speed? Let's show you some brown liquid which does move very fast indeed. It's brown and therefore visible. I shall want here a supply of bromine, which I'm going to put in here. This is 1 cubic centimetre of brown liquid bromine. It's in a glass bottle. We're going to let it loose here in this tall tube. Bromine is a little bit more massive, considerably more massive than air, so that it won't move 400 meters a second or 500. It'll move about 200 meters a second. So it's 700 feet a second. It ought to be up to the top in a seventh of a second. We'll put this in a little container tube like this. There it is. I'm sorry to suck the end of the tube, but it's a standard method of lubricating the rubber tubing. Break his neck. Ready? It'll run down into the tube here, up to the tap, no further. There it is. You can see the brown liquid. I shall say, ready, steady, go, and watch the bromine vapor go up. Ready, steady, go. Oh dear. What's wrong? One word. Air. The air's in the way. The little brown Boy Scouts are trying to move through great big clumsy air molecules, so to speak. They can't get through. What do you need? One word. Vacuum, all right. Next thing is put it on a pump. He says going down, it's helping. We have to be quite sure. We're going to take the supply of bromine. We're going to hope that the vacuum is a good one. I can't be ever sure until too late. Now there is that. Now watch it carefully. We'll first of all break the nose of the bromine. There it is. I shall say 1, 2, 3, go. 1, 2, 3, go. The next experiment I want to show you is to fill a very small sample bottle, which I showed you, with liquid nitrogen. This is liquid nitrogen, which will be boiling away, and we're going to collect it. Why on earth did we have such a big box? We've only got 20 milliliters, 20 cubic centimeters of liquid nitrogen. Well, it'll go up in there anyway. You ready, Mr. Coates? Is it full? Mr. Coates is filling the little tiny bottle, 20 milliliters with liquid nitrogen. I lost about 2 milliliters then, I spilled. The white smoke is just ice crystals. Well, perhaps it's a good thing we had a big box after all. In actual fact, the workshop planned it very carefully. Now, we lost about 10% that spilt out as I was trying to put the stopper on, but we'll allow for that if we like. What's the total amount of stuff I've got? 15 centimeters that way, 10 centimeters that way, 10 that way, if you can see it, and therefore 15 times 10 times something like 80 centimeters. I'm going to add an allowance for that because I did spill some. And I've done this experiment before, and I can assure you it'll come to not far from 100. And I'm sorry it's a round number because it looks as if I was just swindling. I'm not doing that. This plug not screwing. So I'm going to have here 15 by 10 by 100 cubic centimeters. And that comes to altogether 15,000 cubic centimeters from 20 cubic centimeters. And so from 1 cubic centimeter, we divide by 10, and we divide by 2, 750. And so it's a change of volume of 1 to 750. Well, that's not very interesting, but look what we can get from it. Here's a molecule of nitrogen in a little box, because in the liquid state, the molecules are very close together, almost like that. They're very close. And so we can put a little box of side D for diameter of a molecule, D and D. And so the volume there is little d cubed. But when we have it in the gas form, it's a molecule in a prison cell much bigger, and the next one in the next prison cell, and so on. And so now we have large d and large d, and so we have large d cubed, the volume which holds one molecule in gas nitrogen, and d cubed are in the proportion 1 to 750. And therefore d and d are in the proportion of 1 to, what's the cube root of 750? What's the cube root of 1,000? 10. Well, that's too much. Try 9. 9 nines are what? 81. Oh, no, they're not in rough, desperate physics. They're 80. 80, and now multiply 9 again, it's 700 and something. That's near enough, and so we're going to have 9. And so it's d is 9 times little d. And so the story is going to be that the spacing of air molecules apart is 9 diameters of a molecule in ordinary air, such as you see up inside that box. I'm sorry I spilled some, but I just did. We have an experiment which is Mr. Coates's special pride, and it's very good. He's manufacturing liquid oxygen. He's been making it for some time in this apparatus. Oxygen in a cylinder is flowing through liquid nitrogen to cool it, and it is cooled below its liquefying temperature, and so it comes bubbling out here. Here is a dribble out all the time. That's liquid oxygen going on my finger. And there is a lot of it there. Can you see all right? Now we've got a lot more of it here, which I can pour into this goblet. And I don't know whether you can easily see its color. It's quite definitely, what color is it? Blue. You'll see it perhaps more easily with a white card like that. Now Mr. Coates will illustrate the property of liquid oxygen. All right, he's going to take it from there. I promised to say something about how a rocket works. Here is a water rocket, plug in, a water rocket of some kind like this, and it is going to spout out water. Here's the water in a water rocket. It can't be the water pressure that pushes the rocket upwards. It must be something else. It's the air molecules that bounce up and back on the front nose of the rocket. That's where the push is given. The air molecules rebounding from the front nose. Oh, later they push the water out when they get there. But the actual push on the rocket is done by the air molecules pushing on the front nose. And as an illustration of that, I would like to be allowed to have my own rocket cart. So I shall wish you a happy Christmas, and I shall see you, I hope, at next lecture.